co-evolution. Okay, so why we need the evolutionary robotics is that because the environment is changing dynamically, and it is very impossible to and impractical also to foresee every possible state, every possible movement of the robot, all the possible states in the environment. And so that's why we need this evolutionary robot. Then the programming and all, it's very difficult for everything, and the control systems, they are becoming very complex and difficult. So that's why we need such kind of systems, so that we bring to real world only those which are which follow certain rules which are required to, as in we know that they won't fail when coming into the reality.
Sorry, I didn't get the first point. Can you go back?
Why you believe that they will not fail? Because of excessive simulation?
Yes.
What do you mean by robotic system and the environment in which they are placed included?
Because you see, nowadays the autonomous robots, mostly they are used in hazardous situations where humans cannot be used, like mining, nuclear, where the nuclear power is involved, and so on.
So you will put your robot there to evolve, or?
Yes.
No.
She wants to simulate a robot.
Yeah, we
She wants to evolve simulated robot.
Yes.
The fitness function is calculated in simulation.
Yes.
And only after many generations, when they select the best one, they build the body of this robot physically, and they go to real world. This is the idea again.
No, what I mean by this idea is that you have already robot evolved in certain configuration, and then that robot, you can put it in any similar configuration or similar problem, so it can tackle that issue, but not evolving to solve all problems.
Yeah, these are kind of, I mean, for one problem, they implement some one solution.
I mean, for example, if I'm trying to evolve a robot to learn how to walk stairs, for example, I cannot make that the same robot to walk over some pole or something, different task. It always learn how to climb the stairs.
Yeah, you should tell.
With different sizes.
This is always for limited tasks. So
Yeah,
far,
I mean,
even the most advanced methods are always limited tasks. Never for everything.
Yeah, you cannot say.
So they call it artificial life, but it is basically just walking and eating, nothing more.
Yes.
So, if you get my point, I mean, learning here and evolving even the behavior for limited tasks. For example, walking, it will always be walking, not like jumping or evolving to different behavior. Always walking, but with different environment, like with obstacles, like with different size of stairs, stairs with discontinuity, something like that, but not like I will leave it there and they will find, he didn't find the stairs, then he will jump. That's not the way the evolutionary robotics work, I guess.
Yeah, it is made for a customized task, basically, because
from the original one.
Yes.
For example, if I'm evolving to tackle walking, then anything related to walking then will be fine. But something different, then it will be different thing.
Actually, you raise a good point, because I think it is possible to formulate such fitness function that it will work also with jumping. So, in general, you are right that it is always limited task. But walking and jumping is not the best example. Because if the fitness function is just to go far away from a given point, maybe the robot will invent jumping. It's actually a really good topic for research.
Yeah.
Can the genetic algorithm invent a really new gait or jumping when there is some obstacles that cannot overcome differently? Good point.
Actually, today I was about to talk about this, but you stole my topic.
Because this is a class project. Should you finish? You can
okay.
talk. Yeah.
I prepared simulations.
Good, great.
So the first concept was evolved controllers for autonomous mobile robots. So what here they are doing is there are two types. The rule-based system. So certain amount of population of robots is introduced in the simulation, and based on the beneficial traits which are customized for the resultant task. So those kind of traits are then evolved into the next generation, and then after many generations based on the rules, these robots are taken into reality. So that is the first one, rule-based system. The authors, they have explained this using Samuel, which they have done.
Will you show the example of the rule-based system?
Pardon me?
Will you show the example of the rule-based system that is evolved? Are you adding new rules and removing rules, creating new rules, or are you only modifying rules by adding more components to predicates, for instance? What is your evolution?
Modifying the rules.
Okay.
So for the authors have explained it using Samuel, which maintains the population of candidate behaviors and taking the certain beneficial traits into the next generation. And the second one is neural network based control, because neural networks are insensitive to noise, and that's why the nodes are very helpful in maintaining the population and evolving them.
So what you evolve are values of coefficients, or the structure of the network also?
The values of coefficients.
Okay.
Actually, you said the neural network is insensitive to noise. That's not correct. Because neural network can be biased to, and just because of the noise and the data. So I think neural network is sensitive to the noise in the data.
Okay, because
Comparing to what? Are you comparing neural net to other systems?
No, in general. I mean, if I have
In
to,
general, everything is sensitive to noise, but
Yeah.
she wanted to compare to some other method, perhaps.
actually that is they have compared it to rule-based control. So
you're saying that neural net is less sensitive than rule-based
Yes.
system.
okay,
Which
less
is true.
sensitive,
Which is
okay.
true. Yeah.
yes. And there are several challenges in rule-based control, that establishing intermediate goal states is very difficult. Then there are the conflict resolution is difficult in rule-based, and there should be continuous inputs and outputs which should be mapped to the discrete states, which is difficult. So these are some of the challenges in the rule-based control systems. So I found a very.
You remember when we discussed fuzzy logic? This was example of rule-based system where the rules were fuzzy. And earlier I was talking about the rule-based system a little bit, that the rules were binary. But the rules can be also anytime.
Yes.
Multivariate logic, any kind of logic, arithmetic, Gaussian, whatever.
Yes. So this video I found. So you can see there is a worm, and it is kind of in its first generation. So it has like started to walk, and then
I
when
like
it
this
is
music.
evolved.
Trying to fly.
So do you know how many rules? Can you show the examples of rules for this?
No, I'm not exploring that much. but it's learning from its mistakes. If you can. And these kind of systems, they are exposed to more difficult environment, so that this is just a simple example, by the way.
But the question is, suppose that we want to build such a robot. Everyone will be thrilled. It's great, right? But are there any servos that have enough torque that I can actually put to this robot that it will work like this?
Actually,
Is the question.
That's the main
And this is not
challenge.
taken into account in all the simulations.
That's the main challenge, because the degrees of freedom are so many that it's very difficult and impractical to build such kind of a robot.
No. The problem is torque of the motors.
What's on power?
We can build snake like this. This is not a problem. It's not a problem. Problem is, can we have such strong servos and fast servos that I'll be able to get this kind of motion?
Expensive.
Yeah, maybe
Maybe not.
flexible robots can be used, like different technology.
Yeah, but people build many flexible snakes and so on, and I have never seen this kind of jumping behavior, with so much energy.
With servos, it's kind of difficult. It's going to
I
be
don't
very
know
heavy
what
weight
the kids are trying to do. Trying to
move around.
move like a snake or standing up.
No, it is something new. Maybe it doesn't exist in nature.
It's just trying to learn
Tries
something
to
from its
move in
own
some direction.
mistakes.
It should have something. I mean, the objective function of this should be something.
The objective function can be just move in one direction.
Yeah.
Move quickly in one direction.
Direction
Very good.
doesn't matter.
It doesn't matter what. This is the beauty of the genetic algorithm.
Okay, yeah, then that means trying to move toward, but this one is not doing the same thing, trying to stand like a column.
No, it tries just to jump and move in one direction. It's great.
So that's what is the hyper-redundant robot control. Since the degrees of freedom are so high, so it's very difficult to build such kind of robots. They are like analogous to snakes and tentacles. And some scientists, they are doing research on this to study the locomotion and all. Why it is difficult? Because there are many kinematic solutions which can be developed to attain the same end trajectory or the end effector. The next concept they had introduced was evolvable hardware. This one was particularly interesting because what they said that as the environment is very dynamic and it's always changing, the hardware should also change and reconfigure itself according to the environment. They say that it can be done with electronic systems, MEMS, and robots, and obviously it has the potential to significantly increase the functionality, robustness for the robots.
There was one professor in Brandeis University, his name was Polak. He was a pioneer in this area, okay?
Yes.
And he got the grant when the 3D printers were extremely expensive. In 1991 or something, I remember I visited him, he got a very big 3D printer, like a whole cabinet, which costed at this time now $90,000, okay? And what he was doing, he was evolving some kind of shapes, like very primitive legs or bodies and so on, and simulating the behavior like this.
Yes.
Not as sophisticated, but like this. That they were always moving, okay? That's first they were turning, doing something chaotic movement, but then ultimately they were moving. And then when the simulation was good, he was using this 3D printer and he was building them. And then he was coming to conference with a lot of little animals that don't exist in nature and put them on the desk like this, and people were amazed, how these animals were moving. And the simplest animal was just like this. And it was completely evolved by his software, okay? So there was something like this. This was one leg, and here there was another leg, and here was a motor which was just moving this up and down. And this was somehow was crawling. Okay?
Yeah,
One leg
I saw
different,
it.
yeah.
I saw
Yeah,
it.
this
I
is,
saw
this is
that paper.
historical invention. Okay?
Yeah.
Like this one, like three legs.
Yeah.
I saw his paper.
This was very interesting area of research, but then after 1991 there was no great breakthrough. You know, many times in AI you quickly have some great results, you can advertise, it's popular, but the research stagnates.
The next concept that they had introduced was coevolution. So in biology, the body and the brain, it's in lockstep, and it's developed like in coexistence with each other. So it's like that. The robots, the bodies and the brains, they need to be co-evolved depending on each other, so that the body can influence the brain and the brain can influence the body.
Another great example is wolf and sheep, right? When the wolf evolved better, he eats more sheep, okay?
Yes.
But then the sheep has to evolve better to escape from the wolf, right? So many times people simulate the biological system to evolve good behavior of some kind of animal-like robots.
Yes, they had this. Explained this concept using a shepherd and the sheep robots. The shepherd has to rear the sheep from one place to another. So that they had explained using this concept, coevolution.
And also the best sorting algorithm, classical hardware sorter, was built by coevolution. So this area is very practical and has other application, not only in artificial life.
So the next one was embodied evolution. So that's what I explained. In the simulation, they are rearing some population, then they are letting them for interacting with each other, even mate with each other and reproduce. The control programs which are transferred to the next generation of the population, and thus all the beneficial traits, they can get passed on to the next generation, and from then to again the next. And when the best possible traits for a particular task, they are that there are some changes in the motors which are used, then there are some changes in the environment. So it is not always possible to simulate each and every state of the robot, and that's why sometimes what may happen, that the robot might fail in the real environment, or it may show inconsistent performance, or the battery might fail, the poor battery performance, and the hardware might get unreliable sometimes. And these kind of simulations, they run for a longer period of time. So sometimes it may happen that wrong results might be taken for into reality, and not exactly wrong, but previous generations could be taken. So they might not wait for the next generations to come for the better traits, and there might be some modeling errors. Then the performance characteristics of the robots might change, and so it might get unreliable. And now we reach the conclusion that it has great potential to solve many problems in practical life, and the new robots can be developed automatically. And there was also some concept of embodied cognition, where we can develop cognitive models of human performance to augment the robot's reasoning capability. But it is still now in early stage, and I'm hopeful that there will be great discoveries in this field. These are the references which I used. Any questions?
Okay.
Thank you.
I have critical question. Okay. people, tell me, what did you learn really new from her lecture that you can use in some kind of project? Because I have my main criticism that I sent to her already, okay? What did you learn new?
This whole thing was new to me. I didn't know
Really?
anything about applying any of these techniques, so.
But what is new in this presentation comparing to the normal lecture about the genetic algorithm that you know from the class?
Well, I didn't really, I haven't really, other than your class.
It is just illustration, it is just, so far I see only just illustration of the general ideas that I presented in the class. But it could be more, okay? So what I like, okay, your examples were very good, okay? But I think that in the papers there were more technical details that you could go to some earlier papers and show us technical details. How, for instance, you represent a set of rules as a chromosome, okay? Is it a tree, is it a string, you know, I was talking a little bit, and I gave some example, you know? So, I am honest, okay? I think that you kind of flatten stuff, okay? It is good, you are a good speaker, you understand the subject, but there was not enough meat, in my opinion, okay? And I would like that all this presentation will enthuse people, oh, can we do something like this, okay? And in the previous presentation, I saw such elements, okay? So, what I am excited, you know, is this question that arrived here kind of randomly, by chance. Can we evolve the robot that without having the goal of jumping, robot will evolve jumping or some kind of behavior that I cannot predict? For instance, to go up the staircase. And this snake robot, the motion of the snake robot was very interesting. I think it is completely different than any snake robot I have seen. Actually, there are tens of papers about snake robots, and we have a student from India, actually, who had a grant from Indian military to build the snake robot. And building snake robot is not so difficult and not so expensive, you know. You just should have money for like 20 different servos. And the servos can be small. Small servos are $3, okay? The problem is how to control it. But then great, then we don't design any controller, then we just have a separate controllers for every unit, right? For every link of this chain, and we use genetic algorithm. It's very easy. Each chain has some motion like this, 1 degree of freedom, right? So in every moment of time, it is just jumping some angle, right? How can you synchronize all this in a long chromosome that the result will be some behavior? So simulation is more difficult. But now it's also not so difficult because there is, Matthias already has, there is something called physics simulator. So you can describe any system with links, with torques, with powers, and you assume some, you know, like gravity on moon or on Earth, and you simulate the behavior. And then you change the gravity, and you see different behavior of this robot on moon than on Earth. Okay, so it's a doable project actually.
But it's still, I mean, the difficult for student, for even the professional in this field, how to come up with reasonable representation of the solutions, and that kind of choice affect the whole design from the beginning to the end. So I think unless you have experience like 20 years, you will not come up with a good representation to solve.
But tell me, what is the difference of the leg of Jimmy and the snake?
The number of degree of freedom.
Yes, but it's not a fundamental problem. No, you in the leg you have like this 2 degrees of freedom here, 1 degree of freedom here, 3 degrees of freedom here, right? You can do chain like this for 3, and then you can make a chain like this for 20. Okay, and it can be not always symmetric.
But the hidden things here, once you make a lot of joins, that means a lot of data that you are using, cooperating in your
which means the genetic algorithm will take more time to evolve something interesting.
And more time and more power than maybe your Raspberry Pi or the things that you have in that robot cannot handle this computation. There is a limitation. You can do it with computer.
Can't you do it in simulation and just have the final result on the robot?
Use the transfer learning.
If you have good simulator,
it's impossible. I mean, physically, you cannot simulate the robot in all aspects.
Why not?
You have limit.
But you are not simulating all aspects. You are only simulating kinematic chain in the presence of gravity. That's it. It's really not so complicated. There are many papers. I
I know
recommend you to read some of those
there
papers.
are a lot of papers, but what I have seen.
Of course, there is always difficulty in building stuff, taking time and so on, but the concept actually is really simple.
It's possible.